So let's start with our initial idea of a double integral. So if we have double integral of x and y, we have to have two sets of respectiveness for these two integrals, one each, right? And so you have dx and dy in this case, just to keep it really nice and simple. So I'm just going to solve this one just as it's written without moving stuff around first, and then we'll talk about how you can move things around and make your life a little easier. So in this case, it's an indefinite integral. There's no bounds, so we're just going to go ahead and solve this straight out. So we have this function with a partial integral with respect to x first, that's the inside. And then the partial with respect to y goes to the outside. So that's the order we have to go in. Just like in partial derivation, the order matters quite a lot. So in this case, we'll take the partial integral here, so we get x squared times y over 2. That's just the integral of x. And that's still within our integration sign, dy. Okay. So now we can pull this constant out, so we have 1 over 2, and then integral of x squared y, dy. Now in this case, we're going to take the integral of just the y, the x squared doesn't matter, so we have x squared, y squared over 2 times 1/2, and then plus c. Okay? And if you notice, this is x squared, y squared over 4 plus c. Now, what's interesting, if you were a student and you were paying attention, you could notice, or if you didn't realize that, that's totally okay. We'll figure it out. In this case, y is a constant, right? It didn't change when we did this integral. So we can actually just pull the y out, right? And what's also interesting to notice is the x didn't change when we did the y integral. So we can just do y dy and x dx. This is a little harder to get your head around, so don't feel bad if you don't want to try and do it this way. And this only works where you can separate them cleanly and then multiply together. So if you had x cosine of xy, you could do that with the x piece, but the cosine of xy, you can't really split that up unless you are really good at trig, which hopefully you are if you're in multivariable calculus and series for engineers, and especially if you're in electrical. But it's okay if you don't immediately see how that would work out. We can actually work through that example here in a second. But in this case, we can actually do these integrals at the same time. And so we get y squared over 2 times x squared over 2 plus c. And in this case, you would get y squared, x squared over 4 plus c. Exactly the same answer. So that's totally valid. You're totally allowed to do that. And in a lot of cases, it'll make your life much easier if you do. So let's talk about that example I was just saying where you had, for example, the double integral of x cosine of xy. And we'll even add a y term. And we're going to do all of that. We'll do dy dx, because I think that's more interesting. So we have multiple properties we can explore here. Remember that integration is a linear operator, just like derivatives are, and just like Laplace is if you're that far in your curriculum. So you can actually distribute your integrals across the addition sign. So what we can do is we can rewrite this as the double integral of x cosine of xy dy dx plus the double integral of y dy dx. Now the reason that's particularly interesting to us is because we're going to do this idea on both of these individually. So here we have x times cosine xy. Now in this case, because this is an xy coupled, I can't just do them simultaneously like this, but I can still pull this x out. So I can have the integral of x and the integral of cosine nxy dy dx, but because this x is in here, I can't just process this integral of dx immediately. That's unfortunate, but it is what it is. Now on this other side, this is y times 1 dy dx, so I can do integral dx times integral y dy. That is allowed, and that's because this 1 is not at all related to y, and the y is not at all related to x. But because this x and y are related here, that's why we cannot. So this is a really good example to show when you can and when you can't and when you can separate your actual integration instead of just pulling out a constant. So in this case, we do have to rewrite the integral of x because we can't do anything with it yet. Now if we take the integral of cosine of xy with respect to y, that's going to be the integral of cosine is positive sine, so you have sine of xy, and then you divide by the derivative of the inside, right? Or you can multiply by the reciprocal of the derivative, whatever's easier for you to think about. For me, it's easier just to remember to divide by the derivative of the inside. Remember we're with respect to y, so I'm just going to have If I take the derivative of the inside, oopsies, that's just going to be x, right? So we're going to divide by x. And now you can see why it was super important that we didn't process that integral yet, because this is going to affect this guy. So let's finish out our expression. So we have integral of dx is just x, and then integral of y is y squared. Sorry, that's not plus. I apologize. Got ahead of myself. X times y squared over 2. Right? Integral of y squared over 2, and then we'll have a plus c down here. Remember, you should technically be keeping track of your plus c everywhere and iterating them. So like in this example, this is actually like c3, I think, because you had one here and then one here. I guess that's c2 then. So this one's c2 technically. That's not super important for multivariable calculus as long as you are keeping track of there is a constant somewhere. This matters if you have a bunch of like boundary conditions and stuff. So in differential equations, that kind of stuff matters. But for this class, it's not the most important. So here we have an x over an x, so those cancel. So now we just have the integral of sine xy with respect to x plus xy squared over 2 plus c, right? And so in this case, this is C1. We'll call it C1 if we just want to track it just for good practice. So now we just take this integral really quick, which is pretty straightforward. The integral of sine is negative cosine. And then, again, we're going to divide by the derivative of the inside, but this is respect to x. This one's divided by y. And we have plus xy squared over 2. Okay, so here, triple integral, 3 bounds, so you're going to have 3 respectives. A lot of times you'll see dx, dy, dz. Remember that the dx goes to the first, the dy goes to the second, and the dz goes to the third. Now, I saved this piece for the triple integral just because it's more interesting to talk about in the 3-dimensional Cartesian space. You can always swap your bounds around, especially if you're doing indefinite integrals. The only thing is, if you have integration, for example, like this, we have maybe negative x to x, and then x squared plus y, and then x cubed plus y squared. If those are your bounds, this is telling you how to integrate, and you don't want to change these around unless you absolutely have to. You always want to start from your most complicated bounds to your most simple bounds. And in this case, you can see this is most likely dz, dy, dx. And the reason I know that is because these bounds have x and y. So it's most likely that we're integrating with respect to z and then plugging these in for z. And then these bounds only have x in them. So it's most likely that we're integrating with the next term out of these 3 we have is going to be probably y, because then we're plugging in these x's for all of our y's. And then our final term will plug in numbers for all of our x's. And this one's going to be a little complicated if we did it, so I'm actually going to simplify it just a little. We'll just say x plus y squared and x plus y is our bounds there. I think that's a little nicer. And we're just going to honestly leave this function as 1, and we're going to solve this one, because why not? We already wrote it up there. So in this case, we could move them around. If we move them around, we would have to change all of our bounds with respect to our new variables, so that way the last set is numbers. In a definite integral situation, you're almost always going to be asked to get some sort of numerical answer, so you want your last set of integration to be numbers. Okay, so let's go ahead and work on this one. We already know that taking the derivative of a constant is pretty straightforward. Now you may be tempted, using that technique earlier of separating these integrals, to throw this dy in here and this dx in here and say, oh, well, it's just x and y. Unfortunately, because of your bounds, z is related to x and y. So you can't do that with these, and then y is related to x, so you can't do that with even the x term. So you will not be able to distribute your components across. And I'm going to rewrite these a little closer so we have a little bit more space to work with. So dz, dy, dx. Okay, good. So let's start all the way at the top and we'll solve our first integral. I think you can clearly see this first integral is just going to be z. So we're going to have the integral of 0 to 2 and the integral from negative x to x. And that's times z evaluated from x plus y to x plus y squared. And that's still integration bounds, still respective to dy and dx after we do that evaluation. Okay, so let's go ahead and do this evaluation, see how it maths out. So we get x plus y squared minus x plus y. I did intentionally choose the x's to be the same just to make our lives just a little bit easier. So now we have integration 0 to 2, integration negative x to x. Okay, and then x minus x is 0, y squared plus y is just y squared plus y. We can't do anything with that yet. And then we have dy and dx. So far so good, this is starting to work out. Now, again, you may be tempted to try and pull this dx in front, but since the y is reliant on bounds of x, they are related, so you cannot do that. But we can distribute this integral across if we wanted to do these integrals separately. I'm going to do all of that in one step while taking the integral, just because I'm hoping, since we're in calculus 3, that the integral of y squared and the integral of y is pretty trivial for us. So we have y cubed over 3 evaluated from negative x to x, plus y squared over 2 evaluated from x to negative x, and that dx is still hanging out because it still goes with this integral. Okay? So we're going to have 1/3 times x cubed minus x cubed, and then we have plus 1/2 times, this is minus negative x cubed, which does matter, sorry. Okay, so this is x squared minus negative x squared. Okay, good. So this makes a lot of sense, right? We integrated an odd function over negative and positive same bounds, which if you remember from your calculus 2 days, we could have just said that integral was 0 immediately. But I wanted to work it out so you could see it again, just in case that's not something you're super familiar with. Totally okay. So let's do the algebra here. So we have x cubed minus minus, right? So that's plus. So we have x cubed plus x cubed, so it's 2x cubed. Then we have plus 1/2 x squared. So negative x squared is positive x squared. So you have x squared minus x squared, which is 0. I hope that feels okay. Okay, so now we're going to do the integral of this final piece with bounds from 0 to 2, respect to dx. This is where our c is going to come from in this case, but it's still just a c like normal. We can pull this 2/3 out just like we always would, so we have 2 over 3. Integral of x cubed is going to be x to the 4th over 4. And I'm going to evaluate from 0 to 2. Okay. So now we have 2/3, but this 4, we'll just multiply that over, so we'll have 2 over 12. And then we have x to the 4th being 2, so that's 2 to the 4th power minus 0 to the 4th power. 2 to the 4th power is going to be 16, so 16 times 2 is 32 over 12. I think that's right. 2, 4, 8, 16, yeah, that works. Okay, 32 over 12, 32 over 12, those are both divisible by 4. So you get, what is that, 8 over 3? So you get 2.67 if you wanted to use decimal. Totally. So my function here is the function of xy being x plus y. And in this one, we are being asked to evaluate the double integral of that function over the polar rectangular region. Okay, so eval over polar region oh, okay. Sorry, I heard a weird noise. It's just my dog. Okay, the region is r between 3 and 5. Oh man, okay, yeah, r between 3 and 5. That's fine. It gives us our bounds, but that's okay. We still have to convert. So 3 is less than or equal to r, is less than or equal to 5. And then theta from 0 to 2 pi. Okay. So, recall, when you have a polar integral, you always need to get from x's and y's, we need these to be in terms of r's and theta. So we have parameterization terms where we can consider x being our x component is going to be the cosine. So that's r cosine of theta. And then y is equal to r sine of theta. I can do another video a different day about how to get back to these if you don't remember those. It's totally okay. But for right now, I'm just going to assume that you already know this. So if we know that this is true, we have our original equation, we already have our bounds in r's and thetas, so this is actually not too bad, because originally what we were going to have is we had the double integral of f of xy dA, and we want to change that to the double integral of f of r theta r dr d theta. That's what we're trying to do here when we go from Cartesian to polar. So in this case, we're going to plug this in for x and y, we're going to plug it into that, and then we should have everything we need to start solving this integral. So we have a double integral, plugging in x equaling r cosine theta, we have r cosine theta, and then we're going to add r sine of theta. And then all of that, if you notice when we go from dA to polar, from Cartesian to polar, we have to do r dr d theta. That comes from the Jacobian translation between different coordinate systems. There's actually charts of that if you don't want to learn how to do it. If you do want to learn how to do it, I will have to make a separate video because I still have to teach myself that. It was not something that was covered in our curriculum because our faculty did not find it super valuable. They just figured we could just use the chart, which is true. Okay, now remember, our respectiveness is first. So the inside integral is respect to r, and we're given our bounds up here. So we can do this inside integral from 3 to 5, and then the respectiveness for the outside integral is for theta, so we have 0 to 2 pi. Okay? So let's distribute everything algebraically and start solving. So in this case, we're just going to solve, or we're going to throw our r's across here. So I'm actually going to factor out the r from inside instead of distributing this. R in, I'm going to actually factor this r out. So I'm going to have cosine of theta plus sine of theta inside parentheses, r squared outside, dr d theta. Now I'm really hoping that you're already ahead of me and you saw that 5 minutes ago, because that would be amazing. Because what I'm going to do is I'm actually going to pull this out. There's no r inside these. I've completely isolated the thetas from the r's. So now I'm going to separate my integrals. So 0 to 2 pi, cosine of theta plus sine of theta, d theta, and then plus, just kidding, not plus, sorry, did that earlier too, it's habit. So multiplied by integral from 3 to 5 of r squared dr. Right? So we can process these at the exact same time, and I'm going to come over here to do that. So integral of cosine from 0 to 2 pi, and the integral of sine from 0 to 2 pi. This is going to be kind of anticlimactic. Okay. So the integral of cosine is going to be sine of theta, evaluated from 0 to 2 pi, plus integral of sine is negative cosine of theta, evaluated from 0 to 2 pi, and all of that's inside. And then you have r cubed over 3, evaluated from 5 to 3, right? And those are multiplied. Don't forget that they're multiplied, not added, like I keep trying to do. Okay, sine of 2 pi and sine of pi. Well, we know that sine at every positive integer of pi is 0. So that's 0 minus 0, so that's just 0. Gone. Now, cosine of 2 pi we know is 1, and cosine of 0 is 1. 1 minus 1 is 0. And that's why I was saying it's anticlimactic, because those are both 0. Which, if you have 0 times anything, that equals 0. So this integral actually works out to equal 0. But let's solve it. Let's finish solving this out just for the good practice. So you get 5 cubed over 3 minus 3 cubed over 3. And this is actually the reason why I wanted to finish solving this out, is because sometimes people get caught up on not being allowed to use calculators, and I totally understand. But in this case, you really just don't need it. Because 5 times 5 is 25, times 5 is 125. That shouldn't be terrible to figure out, right? And if you're not really sure how to do that, remember that what you can do is, instead of multiplying by 5, you can divide by 2, right? So then that's 2.5, and move the decimal over once. So that's how I got 25 for 5 squared. And then I can do it again, so I get 12.5, right? And then move the decimal over, and I get 125. So that's an easy way to divide by 5 if you're struggling with it in your head. The next thing we're going to do is this 3 cubed over 3. You don't actually have to cube it 3 times, right? What you can do, you don't actually have to multiply 3 times. In this case, that's not that hard, it's just 27. But since you have a 3 on bottom, remember that's 3 to the first power. And when you have the same base, 3 to the 3 can become 3 to the 3 times 3 to the negative 1. When you have the same base here, you can add your powers. So you have 3 minus 1, which is equal to 3 squared, right? Which is 9. So that's minus 9. Okay? I don't really care about the rest of it. I just wanted to show those couple of algebraic things that people sometimes forget or get overly reliant on their calculators for, which is understandable, that you do want to develop some numerical intuition, especially as an engineer. Okay. If we're not sure if we're right about this equaling 0, we can go ahead and solve this the other way. So we can just do this from here. So instead of distributing our integrals out, we'll just leave the integral here of 0 to 2 pi. We'll take the integral of r with respect to r, so we get r cubed over 3 from 3 to 5, and then that's times cosine of theta minus sine of theta, d theta, right? So this was what we were just doing, so we had 125 over 3, I guess maybe I should have finished solving it, minus 9, so that's, we are going to go back to 27 over 3 just to do this math easier. So that becomes 98 over 3, which does not simplify, but it is just a constant, so 98 over 3 comes out front. And now we just have the integral from 0 to 2 pi of cosine theta minus sine theta d theta, which we know for sure that's going to equal 0, because we already did that, right? So it worked out. It still works out to 0, so we know we did this right. So this is a case where separating your integrals can get you to the answer much quicker, as if one of them ends up turning to 0. I've already given this one in integral form, which is, you would think, nice, but we'll see. So our outside bounds are 0 to 2, and our inside bounds are negative root 4 minus y squared and positive root 4 minus y squared. And the actual function itself is x squared plus y squared squared. So x squared plus y squared squared. And in this case, we're doing dx dy. Now, I don't know about you, but that looks like a nightmare in Cartesian. So we're going to convert this to polar, the whole thing. Now, when we do that, we have a lot of things to consider. We have to convert our initial function to polar, we have to convert our bounds to polar here, and we have to convert our respectiveness to polar. So let's do all of it at once. We'll go step by step, figure it all out together. So recall, x equals r cosine of theta, y equals r sine of theta, and let's plug it all in and figure it out. There is a quick shortcut on this one, but I'm going to go through all the math just to show it to you. I'm sure you may already see the quick shortcut if you're really familiar with these kinds of problems, but we're going to go through it. So the first thing I'm going to do is I'm going to convert my function. So my function right now is f of xy is equal to x squared plus y squared squared. So we're going to plug in these guys for x's and y's respectively. So we have r cosine theta inside parentheses squared, and then r sine of theta inside parentheses squared, and all of that's squared. So here, r squared cosine squared plus r squared sine squared, you can factor out your r squareds. So you have r squared, then you have cosine squared theta plus sine squared theta. Now hopefully that looks really familiar to you, because if it does, you'll recognize this just turns into 1. So now I'm left with r squared squared, which is r to the 4th. So our function turns into r to the 4th in polar, which is much easier to deal with. So I'm going to go ahead and write our base structure over here, and we'll start filling it in as we solve things. So we have r to the 4th. Now our next change is going from dx dy to polar, which we already know is r dr d theta. The r matters a lot. The dr d theta can be reversed if it's easier for us. We'll see what works out. So in this case, x is equal, right? Our x bounds are equal to plus or minus the square root of 4 minus y squared. I think this is where I messed up, is by doing it separately. I think this makes more sense. Okay, so we're going to do it that way. So if we square everything to get rid of the square root, the plus or minus goes away also. So you get x squared is equal to 4 minus y squared. And this looks a little more familiar to us because we have x squared plus y squared is equal to 4. Now this is something we definitely know how to deal with. Okay, so in this case, I'm going to erase these bounds because I'm not sure if they're right. Okay, so this is the equation of a circle. X squared plus y squared is always the equation of a circle, and it's equal to the radius squared. So I'm going to write that down. X squared plus y squared is equal to r squared. In this case, r squared equals 4, so r equals 2. So 0 to 2 is definitely right. We're good there. Okay. About the top half of the circle, since we had 0 to 2 for our y, and from the x is a little strange. That's why I don't really know how to show it. But the 0 to 2 on the y is really what's giving me that 0 to pi for my theta. Okay, anyways, back to the math. So we've changed our bounds, and now we just have to solve out. This is pretty straightforward. So you get r5, and then that's going to become r6 when you take an integral. So you get r6 to the 6, 0 to pi, d theta, and then this is from 0, that was a horrible 0 to 2. Okay, so I'm going to pull out 1/3 and then integral 0 to pi because that's going to leave me a 2 here, which I know is a little strange unless you see it. Because what I'm about to have is I'm about to have 2 to the 6th divided by 2. So now I have 2 to the 5th, which is just very slightly easier to deal with. Which is just constant though, so I'm going to go ahead and pull it out. 2 to the 5th should be 32.